All right, I just want to do some of the practice problems in the transformation packet, and even though we've done them in class, I just wanted to go ahead and continue in case anybody was absent. But we're just going to practice some of the different steps that we learned. The first one is to do a reflection across the x-axis. And since our x-axis is the horizontal axis, we're going to be doing a vertical movement. And anytime you do a vertical movement, it affects the y-coordinate. So if A is located at 2, 3, A prime will be located at 2, -3. Okay? So it's going to be exactly on the other side. You do not need to graph these, but except just it might help you figure out the location of where it's moving. Because a lot of people think, oh, well, the x-axis is horizontal, so therefore I'm going to change my x-coordinate. It's just the opposite of that because of the direction you're moving to go across the x-axis. So instead of 2, 3, A prime is going to be at 2, -3. B prime will be located at -4, -1. And C prime, oops, I forgot my little prime mark, will be located at -3, +1. It'll flip from below up to the top. Now then, when we reflect across the y-axis, that's your vertical line, okay, well, we're going to be reflecting horizontally. So that's going to impact the x-coordinate. So if we're at point 2, 3, and we're going to reflect this way, we're 2 away on the other side. So now this point is at -2, +3. So A prime is at -2, +3. B prime, this one will be located at 4, 1. And C prime will be located at 3, -1. Okay, now then, to reflect images that when it's not on a coordinate plane, but you just have a line, I find it easier to make the line vertical so that I can see how the shape matches up to it. And I know that this side right here has to be the same distance from the line of reflection over here. And then this is going to go out kind of this way. And then this point, is going to be about right there in the center. And then you can just kind of connect the dots like so and see your reflection. Not perfect, but just to kind of get the general idea of it. This triangle right here, okay, this is my mirror image. See how this goes down? My vertex should be down over here. This vertex will be on the line. This vertex about right up here. So then we can connect the dots and see the reflection there. But I find it easier to reflect the vertices and then just connect the dots that way. It makes my shape a little more accurate. When you've got the point of reflection going through a figure, okay, just reflect one side at a time. This side here will reflect directly across from it over here. Then these vertices over here will reflect down below. So this vertice should be about here. This one about here. This point about here. And about there. So when we connect them, you have the reflected image. Not my greatest work, but hopefully you get the idea. Okay, reflect the figure on the x-axis. I'm going to reflect each of these points right here. It's 1 away, it's 1 away on the other side. 1 away, 1 away on the other side. Here, I'm 1, 2, 3 away. 1, 2, 3 away. And there's my reflection over the x-axis. You might even see it in the book saying reflected the figure in the x-axis. And I don't know why. I just don't like the way that's worded. It bugs me. But you can see it worded that way, and it means the very same thing. Our little heart here, I'm going to just take it one piece at a time. This little piece right here will be reflected like so. This little piece right here will be all over about there. This little point just over past the 1. Okay, then I can go ahead and kind of connect these And let's see, we've got a point 1, 2 in the middle, 1, 2 in the middle. So we'll go like so. Ooh, that's pretty horrible. But just that one side. Sorry about that. Don't be disappointed. Okay, last one. Number 6. Translate each point right 2 and down 1. Well, if you're moving right, you're moving in a positive direction. So that's x plus 2. If you're moving down, you're moving in a negative direction, and that's y minus 1. Left and right are horizontal moves. They affect the x. Up and down are vertical moves. They affect y. All right, so if my original point is at 2, 3, -4, 1, -3, -1. Okay, and we're going to translate every point to the right 2 and down 1. This is A prime. This point is across 2 and down 1. C prime. Across 2, down 1. B prime. Connect the dots, and there's your new image translated. And don't forget that whenever you have a transformation that it's identical, it's called an isometry. Isometry means it is a transformation that doesn't change size or shape. All right, back here on the next page, we're going to do a few more. You're going to see this one written as x plus 1, y plus 2. So I'm going to take each one of these points and go up 1 and over 2. This point, up 1 and over 2. Up 1 and over 2. So here's this part of my figure. This point goes up 1 and over 2. Up 1 and over 2. Up 1 and over 2. There we go. And then we can just connect them like so. And that's our figure. Now, something I want to go over just to remind you about vectors. This is a translation, okay? But if I wanted to do this in component form, create the vector that moved from this point to that point, you would write it the direction of the movement. I'm moving the x, I'm moving on the x-axis, or I'm moving horizontally, positive 1 direction. And I'm moving vertically, positive 2 direction. This is a vector, which is a direction of movement. And that's what a translation is, folks. A translation is just a movement. And you're moving an image. This tells you how much you're moving it. Okay, now number 8, if triangle DEF is dilated by a scale factor of 3, using the origin as the center of dilation. Now, for all practical purposes, this is what we're going to be doing, is using this origin as the center of dilation. So in other words, we're growing around this point right here. What will be the coordinates of E prime? Okay, well here's point E. E is located at 2, 2. And if I'm using a scale factor of 3, I'm multiplying each of these by 3. Okay, so our new point is going to be 6, 6. So D is the correct answer. That will be E prime. Looking at number 9, suppose the figure is dilated using the scale factor 1/2. What are the coordinates of the new image? Okay, well, what we want to do is go ahead and write down the coordinates of the old image. We've got a point at 1, 1. Another point at 5, 1. I'm sorry, 4, 1, 1, 2, 3, 4, 1. And this is 1, 4. 1, 2, 3, 4. And this is at point 4, 4. Now, I don't have to draw anything over here. I know if my scale factor is 1/2, I'm multiplying each of these coordinates by 1/2. So when I multiply 1 by 1/2, I get a half. So my new point will be half half. My next point will be 2 and half. My third point will be a half and 2. And my last point will be 2, 2. And if we wanted to graph that, we would just go halfway across the unit and halfway up. We would go 1, 2, and then halfway up. A half, and then 2 up. 2, and then 2. So this is our new image right here. It's half the size of the original. Okay, down here at the bottom, it says to draw the image of each figure under a dilation centered at the origin with the given scale factor. Okay, so we're going to dilate this circle with a scale factor of 2. So we want the image to be twice as big. So remember, to change the size of a circle, we're going to change the length of the diameter. This diameter has a length of 4. The diameter equals 4. So the new diameter should equal 8 because it's going to be twice as long. So what I need to do is expand this 2 more this way and 2 more this way. So that has a full length across of 8. Now I can do the same thing this direction. 2 more this way, 2 more this way. And now I've got these 4 points, and it's just a matter of connecting the dots. It's very hard to do to make a pretty circle. But now your your circle is twice as big as the original one. This trapezoid, our scale factor is 1/2, so we're going to shrink it. So this point right here is at 1, 2, 1, 2. So this point is going to be at 1, 1, the shrunken size. This point is located at -2, +2. So we're going to be at -1, +1. This point here is at 1, 2, 3, -4, -2. So we're going to go to -2, -1. This point is at 1, 2, 4, -2. Half of that is 2, -1. And there's our new trapezoid, which has dimensions half the size as the original. Okay? And this is what it means as the origin is the center of dilation. We dilated. You ended up being right around that image. Okay. Now, last page, we've got a rotation, some rotations to do. And if we're going to rotate 90 degrees clockwise, every point is going to be flipped down to the quadrant to the right of it. So this point here is located at 1, 2. So I'm going to flip those numbers down and go 2, 1, and that 1 is negative. Okay, this point right here will be in quadrant 3. It's 2, 2. So we're going to go 2, 2, and be about right here, with this point kind of staying right there on that. Oops, what did I do wrong? I did something wrong, didn't I? I sure did. I didn't rotate this point. Boop, 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 boop. Okay, this point is at 0, -2. So now we're going to go -2, 0. This is what we're looking at. This is our rotation. Yeah, that looks so much better. Okay, rectangle rotating 90 degrees clockwise. So we're going to move this sucker so it's going up like this, and it'll be a standing rectangle. Okay, this point is at -2, -1. So we're going to flip that and go -1, 2. And I had to go +2 because I'm in the second quadrant, and the y has to be positive. This point is going to be directly 2 away over here. Let's go with this point right here. It's at 1, 2, 3, 1, 2, 3. So we'll say 3, -3. we're going to flip those numbers and go -3, -3. Because if you're in the third quadrant, both of them have to be negative. And then this point is exactly 2 away from its original. So you can see its rotation, it would go like this, and then it'll turn and be longer this way over here. Okay, this diamond. Okay, this diamond is at 1, -2. So I'm going to flip that. And I'm going to go -2, 1. But since I am over in the third quadrant, my y-coordinate needs to be negative now. Okay? So -2, -1. All right. This point right here at +2, 0. So that will be at 0, 2. Oops, what am I doing? This point, 0, -2. My bad. All right, this point will be located right here. This is at 1, 2. So now it'll be at 2, -1. I know I flipped these, and I know that I'm going to be in the fourth quadrant where y is negative. So 2, -1. And then, let's see, which one have I left to do? This one right here? This one that's 0, 0? It's going to stay at 0, 0. Booyah. There we go. There's our rotating diamond right there. Okay. And then, symmetry. Which of the figures below have rotational symmetry? Okay. This particular image, as you can see, has an empty piece and then one that sticks out. So that when you rotate this here, this empty piece will open up there. This will go here, and this empty piece will go there. So this ends up having 90-degree rotational symmetry every 90 degrees. So 90, 180, 270, and then of course 360, but every 90 degrees. If this is an equilateral triangle, which we're going to assume it is, then we know that these angles are all congruent. So when we rotate this, these angles will all map onto themselves because all of these lines are congruent as well. So we've got 360 degrees with 3 angles that will map onto themselves. That gives us 120-degree rotational symmetry. So 120, 240, and of course 360. This trapezoid. The only way this trapezoid will map onto itself is if it turns all the way around, because this angle has to come back and map onto itself because these lines are congruent but they're not parallel. So when we turn this upside down, these lines that are now going down will be going out. Oops, that was kind of stupid. It will be this way, like so. So it's going to be just the opposite. It will not lay onto itself. So this has no rotational symmetry, except for 360 degrees. And I just want to remind y'all that everything has 360-degree rotational symmetry. This one has none, because there's no way you're going to have this empty little corner. So when you turn this image, there's supposed to be something there, but we're going to end up with an empty corner. So it's like if you were to trace this image and turn it, would you ever see any of the tracings? And if you do, then it doesn't have rotational symmetry. This particular image, if I turned it 90 degrees, it would have no rotational symmetry. But then if I turned it another 90 and went 180, we'd be good to go. It would definitely map onto itself. So it has 180-degree rotational symmetry, as well as 360. You know, it's kind of redundant to write 360 because we know it does. All right, this 5-pointed star, it's got 5 points that are identical. So if you were to take 360 and divide it by 5, you would get 72 degrees, which means every 72 degrees, this will rotate and map onto itself. So 72, 144, 216, 288, and then of course 360. This would be, if we started here and rotated 288 degrees, we'd end up right there. All right, last but not least is the line symmetry, where we can split it, a figure not just in half, but in half so that it is a reflection. So it's like a line of reflection. The letter A, you can draw one line right through the center, and then the left side and the right side reflect. B, you can draw a horizontal line. C, a horizontal line. D, a horizontal line. E, a horizontal line. F, none. No lines of reflection. No lines of reflection for G. Now H, I can draw a vertical line and I can draw a horizontal line, and it will reflect vertically and horizontally. I, same thing, I can split it down the center this way and this way. None for J. Now this particular K, no. But let's say you make your letter K's like this. Okay, so they look exactly alike. You could do horizontal symmetry there. L, no. M, right down the center. N, nope. O, now the thing about O, it's got infinite lines of symmetry, because I can just keep cutting this in half, and guess what? I've got a semicircle every time. P, none. Q, none. None for R, none for S. T, I can cut it lengthwise down the center. Same thing with the letter U and the letter V and the letter W. Now, the letter X, we can do vertical, we can do horizontal. I can also cut it this way and this way. So there's 4 lines of symmetry there. The letter Y down the center, and Z, nope, nada, zero, zilch. And that's it for the practice problems in this packet, folks. So I hope you learned something.